So here's the plan. 3 parts. I'm going to start by telling you about Ackermann compressed integers and computing with them. So this will be, and then I'm going to tell you about the word problem and Dehn functions, and then bring these together in a section called Taming the Hydra, which will be about using some of the things, these Ackermann compressed integers and algorithms for them, using them in group theory. So I'm a visitor from a foreign land. I work in group theory and topology and geometry, but I'm very happy and excited to talk in computer science, combinatorics sort of, forum, because a lot of some of the things I've been thinking about recently and for a while impact or relate to computer science, but I've never really unleashed them on genuine computer scientists. So I'm intrigued to hear. Maybe you can fill in. So I'm going to give you lots of background in section 2. Section 1 is going to be quite short, and if there's background, maybe you can tell me about it. Anyway, we'll see. Section 2 is mostly expository, and section 3 will be applying this. Anyway, let's get on with it. So Ackermann compressed integers. So I want to start with Ackermann. So this is to do with Ackermann functions. There's Wilhelm Ackermann, who was a student of Hilbert. He defined this family of functions. There are slight variations on how these things are defined, but here's one way it appears. I'll write this down on the board because we'll refer back to it a number of times. So start with the function a1, which is just the doubling function. We'll define it on the integers. And then we're going to use a recursion to define the subsequent functions. This recursion, we'll define them on the natural numbers, and we'll start at 0. They'll all equal 1 when, at least when I is greater than or equal to 2. So the recursion, so AI is on the natural numbers, and it's ai plus 1 of n plus 1 is ai plus 1 of n, right? So the way this works is, we start with a1, so put in the first row here. We fill in this column because we've defined all the functions to be 1, to take the value 1 at 0. And then we can fill in the table using the recursion. And it goes like this. So the recursion says, for example, why is there an 8 here? Well, you get that by, you look 1 to the left, you see a 4, and so you go up 1 row and you look at the entry under 4, and it's 8. So that's how this works. And then the next row, so for example, 16 is here because you look 1 to the left, there's a 4. You go 1 row up, you look under 4, and you see 16. So this, so we start with the doubling function. The next, that's a1. The next function's iterating the doubling function, so it's n goes to 2 to the n. The next one's iterating that. It's a tower of 2's, and we get increasingly fast-growing functions, extravagantly fast-growing functions. I want to also have just, this is going to be a convenience, which will, when we come to group theory a lot later, we'll see it's sort of natural. Yes. So I also want a0. So for convenience, we'll let that be n goes to n plus 1. And I'll define inverses of these functions. Now, these functions are all strictly increasing, so they're injective. So we can define inverses, at least on the images. Okay. And we can use these functions to express integers. So I want to fix a k. That's going to, because I want to work with a finite alphabet. So we're going to work with the alphabet A0 through to AK and the inverse symbols too. And we'll say, well, a word on these symbols can represent an integer, and it's going to be take the word and evaluate it at 0, just with composition of functions. So for example, this word here, A1 inverse A2 A0 3, we plug in 0 on the right, and this evaluates. So you apply A0 3 times to 0, you get 3. You add 1 each time. Then you apply A2. A2 is the function n goes to 2 to the n, so we get 2 cubed, which is 8. And then we apply A1 inverse, which is the halving inverse of the doubling function, halving function, so we get 4. Okay. Here's another example. A0 to the A3 applied twice, and then A0 applied 4 times. So you apply that, you get 4, and then you want to apply A3 twice to 4. Well, A3 is that tau function. You apply it once to 4, you get that, and now you want to apply it again to that. Well, it's something, enormous. So very short strings can represent massive integers, massive compression. But of course, the integers that are highly compressed here are very rare, because if you're working with an alphabet on 2k plus 2 symbols, if you've got a word of length n, you can only have exponentially many different words of different words of length n, and so they can only represent that many integers at most. And but these functions are growing far faster than the exponential functions, so the highly compressed integers are very rare. But they are some of them very big. Let's look at this example. So A2 inverse A1 to A0 3. What happens when we evaluate this one? We first A0 applied 3 times, so that gives us 3, and then you apply A1 twice. That's doubling it twice. That gives us 12, and then we want to apply A2 inverse to 12, but A2 is the function n goes to 2 to the n, but 12 is not a power of 2. Say invalid, doesn't work. Okay. Okay, so theorem about this. We can compute with these things in a very limited, in a limited manner. We can decide in polynomial time in the length of the word. This is the word on the symbols, as in the last slide. Polynomial time, where the degree of the polynomial depends on the size of the alphabet, depends on k. We can decide whether w is valid, and if it's valid, we can decide its sign, the sign of the integer it represents. Because yeah, and you can double them to make them more negative.
So you extend it out.
Well,
A1 is defined as a.
right.
Okay.
That's a bit quirky, but it turns out to be the right thing in the end. Okay. yeah, inverting +1.
Just
Yeah.
So in particular, only if the word starts with A0 or A1.
Right, you could have it later.
Then you can apply AI to a negative number.
Right. When I
So the word has to start, and it starts with or end with A0 or A1.
well, you could make something positive and then subtract 1 from it many times to get negative.
Yeah, so it starts from the left. The left. Seems like that's not the point.
Okay, so
What about, so given two words, deciding if one is bigger than the other?
good question. I don't know how to do that. So I want to give you a feeling for how we do this. Yes. Oh well, everything's computable here. You're right. You can evaluate, but the point is polynomial time, right? Because you really don't want to evaluate everything because some of the integers represented are so enormous. Well, I just want to know. It's enough to know, for the purpose, which ones are valid, and which ones, and if they're valid, what's the sign? Is it 0? Is the thing evaluate to 0, or is it positive or negative? And you could use that. So if you wanted to know whether it equals 10 or something, you could do this. You could. This one. Right. So I want to give you a feeling for how we do this. I'm not going to just describe algorithms to you. It's horrible. But I'm going to just describe a few salient inputs and how we deal with them to show you the key techniques. So so here's a word W. And it's got length 17, and it's not a random example. It's chosen not to have any inverse letters apart from a 0 inverse. Now this is a particularly nice situation for some of the reasons I think we were alluding to, because well, first of all, think about validity. First of all, the obstacle to validity is you're feeding a negative number into one of these things. But these are not present in this example. So suppose you just start evaluating this from the right.
A1 is n goes to 2, but you want to stay in the integers.
Right.
But you also can't feed negative values to A1, right?
You
Sorry, to A2. A2 and A3.
right. Yeah.
So that's another one.
Yeah. So suppose we just evaluate this from the right. So A0 of 0 is 1, and then A2 of that is 2 to the 1, that's 2. Then double it, you get 4. Then 2 to the 4 is 16, and subtract 4 is 12. And then next we want to hit it with A5, but we don't want to evaluate that. That's crazily big. But we've noted that the length of this word is 17, and that's a sort of threshold. We know A5 of 12 is bigger than 17. You don't have to compute A5 of 12 to know that it's bigger than 17. You can do some pre-computation. You take the word, read off its length, and you can write down all of the values of our table of Ackermann functions, which all the ones where which evaluate to less than the threshold, less than 17. That can be done very quickly and efficiently. So you get to this point, you know this is bigger than 17, and then everything that follows couldn't possibly bring it down to, couldn't bring us back down to 0. There's just not enough. The only thing that decreases the number is A0 inverses. So we exactly. So we don't get down to 0, and we yeah. So we conclude this is bigger than, that's bigger than 17. So this is valid, and the word evaluates to something positive. Okay, good. So this is a situation we should in general aim for. So suppose we have this example. So this has an A2 inverse in it. Can't do the same trick. But what we'll try and do is cancel this A2 inverse with an A2 that comes later. So yes. Right, and also there's the issue of if it was valid, then exactly how it evaluates might affect what the sign the thing eventually has. If it's valid, it's well. Oh, in this instance, but only because there's not much to the left of the A2 inverse.
The first negative is A2.
No, you could then have A0 to the minus a million, and take as negative again. Okay, so the strategy, the next strategy is sort of peak reduction. We try and cancel. We look for the rightmost AI inverse where I is at least the rightmost AI. Just the rightmost AI inverse where I is at least 1. So in this case, it's A2 inverse, and we try and cancel it with a subsequent AI. In this case, an A2. So how do we do that? Well, we make some substitutions. We try and we convert the word into what we call an equivalent word. Equivalent means that two words are equivalent when they're either both invalid or they're both valid and represent the same integer. So passing from one word to an equivalent word doesn't change up the problem we're facing. So these are equivalent. So what have we done? What have we done to go from here to here? We've replaced A2 inverse by this, right? And this is based on this. This says that taking log to the base 2 is the same thing as halving, then taking log to the base 2 and then adding 1, right? And such substitutions are not always allowed. This is not quite like group theory where you can manipulate words, as we're going to see later. Right, so there's a condition on what you're feeding in to make sure such a substitution's allowable. But that's something you can check using the technique on from the previous example. And anyway, we make substitutions of this sort of form to try and bring this A2 inverse close to this A2. So in this case, we can cancel off an A1 inverse with an A1. Again, we've got to think carefully that's a reasonable thing to do. And now we've got to a situation where we have an A2 inverse. It's a bit closer, but between them is just a power of A0. So we've got a function here, n goes to 2 to the n, then we're just adding 8, and then we've got log to the base 2. Now, with this is in this sort of situation, you know, the image of A2, the image of the function n goes to 2 to the n is fairly sparse. So for this to be valid, the number you're adding here, assuming we've fed in something reasonably big, this number has to be pretty big in order to bridge the gap between two numbers in the image of A2. And so direct calculation becomes a viable, computationally reasonable thing to do again, because the length is the length has to be big in order to get from here to here, and and then in fact, so you can directly calculate this and conclude, it actually represents 6. It's valid and is greater than 0.
So this could considerably work with any sufficiently fast-growing sequence function.
Right.
That could be this sequence Ackermann.
Right. Yes. Well, we use the substitutions to bring things close. That really used this recurrence. I agree. I'm not going to tell you the algorithm in detail, but I see your point. Yeah. Yeah. So valid is when you evaluate from right to left, you never, at every step, you don't run into a problem of feeding, of trying to evaluate one of these functions feeding in as something not in its domain. We always start with 0. We always feed in 0. Right. But yeah. So here's another example. So this is an example where we've got here's the rightmost AI inverse where I is at least 1. It's an A2 inverse, and we want to cancel it with an A2 somewhere to its right, but there isn't one. All right, and so you manufacture one, in this case, by using a substitution as before. Right, but validity could be a problem. So here we make this substitution, which again is derived from the recurrence relation, and we're trying to bring this A2 inverse to cancel with this A2. It turns out we make more substitutions to do this. This time we're substituting this A2 for that and this A2 inverse for that. We get to this point, and at this point you can realize you're in trouble because this is a doubling function, this is subtracting 1, and then this is dividing by 2. So whatever happens up to here, we must run into trouble here and get invalid. Okay, so those are some of the ideas. I'm not going to give more details on those algorithms. It's not pretty, but I hope it's about 10 pages. Yes. Why was Ackermann interested in his functions? I think it was it, you probably know, is it the early days of...
They were interested in what is computable.
Right.
And, they were trying to see which properties of computable functions to prove of. It turns out that these grow faster, that these functions grow faster. You cannot prove the statement about them in general. They are not primitive recursive.
They bridge from primitive recursive to recursive. If you take each of the AIs is primitive recursive. But the diagonal n goes to an of n is not primitive recursive, but it is recursive. Okay, so now some group theory background. The word problem and Dehn functions. So the word problem goes back to it was published in 1911. Max Dehn, another Hilbert student, incidentally. So he wrote an influential paper in which he identified 3 problems as key if you're studying a group that is given with a finite list of generators. And the first of these problems is what we now call the word problem, or here it's the identity problem. So an element of a group is given as a product of generators. One is required to give a method whereby it may be decided in a finite number of steps whether this element is the identity or not. So I think one thing that intrigues me about this is his writing in 1910. It's a pretty good idea of an algorithm. Anyway, so we now interpret this as give an algorithm. Hilbert what?
Finite number of steps to decide in a finite number of steps whether.
Oh, it's solving equations.
Yeah. For example.
Huh.
Yeah. So it's after it.
Okay, so that's the word problem, and Dehn functions is sort of an intrinsic computational perspective on the word problem. So this is specific to finitely presented groups now. So we've got gamma, a finitely presented group, a finite list of a finite list of generators, and a finite list of defining relations. So oops. So the group is the free group on the generators, quotiented by the normal closure of the defining relations.
The relations are just words in the elements of A, and they are defined to be like that.
Right, things you want to kill in the group. So free. Right. Yes. Yeah. For instance. So that would just be a list with a single defining relation. So then we'll define, so the Dehn function we're going to call area for reasons we'll see in a minute. Area at a natural number n is defined to be, so it's a worst case, think of it as a worst case complexity measure. It's the maximum of areas of words. One here is the identity. This is. Oh, sorry. Yes. Yes. Thank you. Sorry. Yeah. So it's the. You look at all words on the generators and their inverses that have length, yes, at most n, and represent the identity, and we look at their areas. And what we mean by that is, well, first I'm going to give you this in a number of senses, but first in a computational sense. It's the minimum capital N such that you can convert your word W to the empty word by using the through steps, each one of which uses the just uses a defining relation. So so there's a sequence starting with W, ending up at Wn, which is the empty word, and you go from one thing to the next in the sequence by it's applying a relation, and then you can also do some free reduction if you like. Free reduction just means cancelling away inverse pairs of letters.
And those do not count towards the end.
They do not count. Yeah. Well, if the word represents the identity, which then it will do as a consequence of the defining relations, and this is one sense in which that's true. Exactly. So it's sometimes called the Dehn proof system. So just to be clear, what I mean by applying a relation, so you go from Wi to Wi plus 1, where so Wi is some prefix times some subword alpha times some suffix v, and you convert it to, you replace that alpha by a beta, some other word, and this is where alpha times beta inverse is one of our defining relations, or the inverse of a defining relation, or in fact a cyclic conjugate of one of these things. Right? That's applying a defining relation. And you asked for an example. Yes. So think about a nice easy example is z cross z. So just one relation, AB is BA, or that will express it as that commutator if you like. And here the Dehn function is grows quadratically, because suppose you had a word on A and B that represents the identity. How do you convert it to the empty word? Well, you shuffle A's plus B's to bring the A's together with A inverses and the B's together with B inverses. Because shuffling A's plus B's is applying a defining relation.
So the word would be A to the N, B to the N, A to the N inverse.
Say it again, A to the...
It would be NA, then NB, then NA inverse, then NB.
That would be the worst word. That would be the worst word, yes. So the upper bound is, every A has to be shuffled past at most n B's or B inverses, so to bring all the A's and A inverses together to cancel them away, right? So that's n times n. That's the n squared upper bound. Yeah. The lower bound is, as RV says, is the square. You can't do better than n squared with that. I'll give you a geometric reason later. Okay, can I go on? So what's this got? What have these two things got to do with each other? The Dehn function and the word problem. For a finally presented group, the following are equivalent. The word problem is solvable. You can find an algorithm that solves the word problem. The Dehn function is bounded from above by a recursive function. So why are these two equivalent? Suppose we've got a recursive upper bound on the Dehn function. I give you a word, and you want to know whether or not you want to know whether or not it represents the identity. Well, suppose it does represent the identity, then feed it into our upper bound, feed its length into our upper bound for the Dehn function. That gives me a bound on the number of steps I'd have to take in this proof system in order to reduce it to the empty word. So I can just try all the possible ways of doing it up to that bound. Extravagant, but works. And so I get a solution to the word problem. If the thing represents the identity, it will be reduced to the empty word within that number of steps. If it can't be reduced in that number of steps, then it didn't represent the identity. And the other direction, suppose the word problem is solvable, then how do we show that, well, actually we could show that the Dehn function is a recursive function. How do we do that? So
Your algorithm stops and it's running time of algorithm.
right. So you look at all.
When you say solvable, it means by this replacement.
Right. You look at all words of length at most n. The word problem. You've got a solution to the word problem, so you can weed out all the ones that don't represent the identity. And so you just restrict your attention to the ones that represent the identity, and then you can start listing all possible ways of trying to reduce those words to the identity. You know that they represent the identity, so you will eventually find ways to reduce them to the identity. So the Dehn function actually, so you can tell which one you can find the most efficient. No.
We have to know for what it is it's the only way to solve the problem is to apply it. Maybe there is some way.
No, we don't need. Right, that's an issue we're going to come to later. But for this, we don't. For this, that's not an issue.
The validness question is what prevents the algorithm from taking the outside function of the word.
Something different.
Why can't you solve the word problem in a more intelligent way? You can. In many circumstances, you can. We'll get to that later.
No, more intelligent without
The question is why it's recursive.
Right. So which way do you want to go? If you can solve the word problem, do you want to prove?
I assume that I can solve it.
Okay. So let me tell you how to compute the Dehn function. Take the set of all words of length at most n, right? For each of them, solve the word problem. So now to throw out all the ones that don't represent the identity, and now we're going to calculate the area of every single one that remains, and right. This we know that they can be reduced to the empty word. So find. Yes, exactly. Yes. So in fact, yeah, these three are equivalent. Okay. Okay. What about a geometric perspective on this? So this is all to do with soap film geometry. So classical fact: Euclidean space enjoys a quadratic isoperimetric function. The Greeks knew this. If you have a loop in Euclidean space, you can span it with a disk that has area at most constant times the length of the loop squared. Constant is something to do with pi. Okay, so more generally, if we've got a loop in a simply connected space, let's say that the area of the loop is the infimum of the areas of disks spanning the loop, where area means anything reasonable you like, Lebesgue, whatever. Let's not go into that. Provided that if the space is reasonable for this to exist. And then you can define an isoperimetric function, which is so defined on the positive reals. So feed in a real number L, and it's a worst case thing. So look at all loops of length at most L, and look at what's their take the supremum of their areas. so let's go from that sort of, maybe that's most natural in sort of Riemannian geometry. Let's move from that to a more group theoretic sort of combinatorial setting. So here's a disk spanning a loop in three-dimensional space. Think of three-dimensional space as tessellated by unit cubes. So we're really thinking about the group Z cubed. And you could imagine pushing this picture, pushing the loop into the one skeleton and pushing the disk into the two skeleton. And what we have, and then we've got a very straightforward notion of area, namely count the number of two cells. And what we have is called a Van Kampen diagram. So we're working in Z cubed. This is a picture of a Van Kampen diagram for the word you read around the outside, where you consider you've got three types of edges. Edges to the right are B's, edges this way are A's, and edges up are C's. So around this loop, you're reading, which way did I do it? B. Oh yeah, B. Yeah, right this way. B A minus 1, C A inverse, and so on. This word around the outside, and the cells here correspond to defining relations. We've got here are the three defining relations that in this group. It's A and B commute, B and C commute, and C and A commute. And this is a this planar diagram is a cellulation of a disk, or in fact a singular disk. It's not a topological disk. It's cellulated by these cells in such a way that the edges match up, sort of jigsaw puzzle, but with flexible pieces. And in general, a Van Kampen diagram for a word is a finite planar contractible two complex. That just means a singular disk with edges directed and labeled so that around each two cell you read a defining relation, and around the boundary you read the word that it's a Van Kampen diagram for. So this is a visual proof of how it is that this word represents the identity, follows from the defining relations, and it corresponds to a homotopy disk. It corresponds to a disk spanning a loop in this space. This is completely general. If you've got a group gamma with finite presentation that, and you've got a word W, then the word represents the identity in the group. Well, what does that mean? That means the word is in the normal closure of the defining relations. That is, the word can be expressed, or the word is equal in the free group on the generators. It's equal to a product of conjugates of defining relations and their inverses. That's what it means to be in the normal closure. And that's the same thing as admitting a Van Kampen diagram, because you can take this product and draw, it's called a lollipop diagram. Think of a base point here, and I've got a sequence of edges so that reading that way, they're labeled by, you should think of this as a sequence of edges where they're all labeled by generators, elements of A, and directed, so that when I read it that way, I read U1, and then around here I read R1 to the power of epsilon 1. Anyway, so when I read around the whole perimeter, I'm reading this product. And but if this equals W in the free group, that means if I do some free reductions and free expansions, then I should reduce the word around the perimeter. Free reductions and free expansions, well, free reductions correspond to gluing some edges together, pairs of edges together. And that should collapse this diagram down to something which has boundary the word W. So it's like folding it up, and you end up with a diagram, a Van Kampen diagram. Now, there's an awkwardness here about, do you really maintain planarity as you do this folding? Technical details I'm not going to go into, but admitting a Van Kampen diagram is equivalent to representing the identity. Okay. Yes. And the area of the word, we've now got three senses for area, all equivalent. The area of the word, it's the minimum number of it's the minimum n that occurs in this product. It's the minimum number of faces in a Van Kampen diagram, and it's also the minimum number of steps in that Dehn proof system. So what's the Dehn proof system got to do with this picture? Well, so we've... Yes?
If your word is just some second permutation of one of the relations, then what is the area?
1.
But there is not 1, so you need to take
All right. So what's in this picture? What's this got to do with the Dehn proof system? Well, applying a relation is pushing the boundary loop across a cell. That's how these notions correspond. You eliminate one cell at a time. Okay. And this, and these Van Kampen diagrams in general serve as homotopy disks in appropriate spaces coming from finitely presented groups. So if P is a finitely presented group, then the appropriate space is called the presentation 2 complex. This is the space in which we fill loops, and Van Kampen diagrams serve as homotopy disks. Well, sorry, it's the universal cover of this. So we build a presentation 2 complex like this. So you have a single vertex. You have a loop, one loop for every defining relation, directed and labeled. Then you attach a cell, one cell for each defining relation, and you use the defining relations to determine the attaching maps. So we get a little finite 2 complex, and the universal cover of that is the fundamental group of that is the group presented by P, and the universal cover is called the Cayley 2 complex. So there's a simply connected space in which we can consider filling loops. And the one skeleton of this is the Cayley graph, not in the sense you were talking about yesterday. Not so far away. But, okay, one skeleton is the Cayley graph. Of a finite complex, yes. Here are some examples. Suppose this group here, this is, well, so you've got 4 defining relations. So we've got a single vertex, 4 loops, and we're going to attach one cell, an octagon. 4 generators, 1 defining relation. We're attaching the defining relation. It's an octagon. We attach it. What do we get? A genus 2 surface. Universal cover is pictured there. Naturally, it's naturally thought of as a tessellation of the hyperbolic plane. Yeah. So you attach this octagon to this thing here. So this is a single vertex and 4 edges, each of which are loops. And then you attach this by so you glue it to matching up the arrows. All 8 vertices go to this vertex, and all the edges are glued so as to match up with these. It turns out in this instance you get a surface of genus 2. It's quite pretty. And that's the universal cover. Here's the free abelian group of rank 2. This time it's a torus. And the universal cover is like plain tessellated squares. Here's another example. So another one related group. It's quite hard to picture this time what you get when you attach that to that. But its universal cover looks like this. So this is well, viewed from over here, it's a trivalent tree. So it's a trivalent tree cross a line, and you've got these combinatorial hyperbolic planes sweeping up, and there's one at the front here, and then they come in from behind, and they branch off each other, and they join along these vertical lines. This is called Bam's-like solitary group BS12. Okay. And then we can take the notion of isoperimetric function and define it in this setting. So you've got an edge loop in the Cayley-2 complex, and the area of the loop is the minimum area amongst all Van Kampen diagrams spanning the loop. And then the Dehn function, you can define this way, is you take the maximum. So at n, it's the maximum. You look at all edge loops of length at most n in the Cayley-2 complex, and you look at their areas. The thing I showed you at the beginning with moving from the soap film world of Riemannian geometry to this combinatorial group theoretic setting is in fact really general, and that the theorem that catches it is sort of due to Gromov, but other people had to fill in all the details. So it's
All of the Gromov theorems.
careful, this is being recorded. Okay, so this says that if P is a finite presentation of the fundamental group of a closed Riemannian manifold, that is a compact Riemannian manifold without boundary, M, then the isoperimetric function of the universal cover of that, it grows in the same way as the Dehn function of the presentation. So that picture I started with of taking a sort of soap film loop, a loop spanned by a soap film in R cubed, and pushing that to something combinatorial in Z cubed, that's what's going on here. That's entirely general. That intuition can be developed painfully into a proof, a careful proof, and this is the general statement.
So this is up to constants.
This is up to constants. To be precise, I put it in, here's the footnote. It's up to an affine distortion of the range and domain. There, up to lots of constants. And it's natural to have lots of constants here. For instance, the Dehn function was defined, I defined it for a given finite presentation, but it's really a group invariant. If you change the finite presentation, but you stay with the same group, you get an equivalent Dehn function. The function grows in the same way, also in the sense of this equivalence, which is in the footnote. And indeed, there's more you can say. These functions are quasi-isometry invariants. That means they're coarse geometric invariants, large-scale invariants. So the quasi-isometry invariants amongst the space of amongst finitely presented groups. If you've got two finitely presented groups and they're coarsely equivalent in this quasi-isometric sense, then their Dehn functions grow in the same ways. If one's quadratic, the other's quadratic. If one's exponential, the other's exponential. And to go back to these pictures, no, this is not just two-dimensional. And this is about any closed Riemannian manifold, or equivalently about any finely presented group.
What is how can you get in groups?
The world is a one-dimensional group.
Right.
The world is doesn't matter.
There is maybe the word, is the word isoperimetric, is the word isoperimetric the confusion here? Because I know it's used in multiple senses. This is all about filling loops with disks, but it doesn't have to be, the space in which you're doing it doesn't have to be two-dimensional.
Right. So when you start with a manifold, just take it to the
Right. I mean just filling loops with disks. Oh, no, any dimensional. Well, greater than 1. Yeah. So the three torus, so the universal cover there is, you think of as Euclidean space tessellated by unit cubes. Yeah, right. That's all right. You can picture it, can't you? The Euclidean. So there, we're comparing, just filling an arbitrary loop in Euclidean 3 space, spanning that with a disk. We're comparing that to taking an edged loop in the one skeleton of that tessellation and spanning that with a combinatorial filling disk, a Van Kampen diagram, that lives in the 2 skeleton, and where area there just means count 2 cells. And the 2 functions you get agree.
So it's all diet adaptation questions or subject, right? Because, I mean, the Dehn function only depends
on the we've been talking about filling in simply connected spaces, so that's why I've been taking universal covers.
No, but I mean, if you take 2 manifolds with the same universal coverage, then you get the same. So you can move from a fundamental to any covering of it.
But you need to have the you need to have the group act on it. You need the quotient to be compact. So we started with our manifold M was closed. That means compact without boundary. So what you say is true, provided that the quotients are compact. And in that case, the groups would be quasi-isometric, and the Dehn functions would be the same, or grow equivalently.
Is it known what kind of functions can be done?
You're anticipating the next part of my talk. Let me finish with these 3 examples, and let's have a break, and then I'll go on to that. Okay? So. Right. So you need a detail in the proof of Gromov's filling theorem. So what you do is so we've got our manifold M that's compact. We look at its universal cover. The fundamental group acts on the universal cover by deck transformations. Take a base point and in the universal cover, look at all its translations by group elements. So that's going to be some discrete set of points. So that corresponds to the group, and then join up those points by edges when you can so as to embed the Cayley graph in, right? So that is join them up when you can join them up by geodesics in the universal cover of the manifold when when the corresponding group elements are related by a generator, right? And then put in cells to make the Cayley 2 complex sitting inside your manifold. So you do, and you do it in a translation invariant manner. And so there you've got a 2 complex that's then sitting inside your universal cover of your manifold, and that is what you push a general filling towards to make a combinatorial one. That's the outline of the proof of filling theorem. So just to finish this part of the talk, the examples from before. So the Dehn function here turns out to be linear. Here it's quadratic. So these facts correspond to the classical results about isoperimetry in the hyperbolic plane and in the Euclidean plane, linear, quadratic. And here's an exponential example, and that's because so you get Van Kampen diagrams that look like this. So remember, these are these hyperbolic planes that there's one sweeping up the front here, and there are more at the back. And if you took, say along this line, you've got this plane joining with another one that's going off down below. If you take a path like that on this in this front plane, right? And then in the back plane, just go along a small distance, one in this horizontal line, and then go around a similar path in the back plane, and you get something which a loop which can be spanned by a disk that looks like that. Right? Can you imagine how the bottom half of that goes into one plane and the top half goes into another? And that's and there's the doubling pattern apparent in this. That's where this exponential comes from. Right? And actually, there's a geometric way of getting lower bounds that's apparent here. So these are dimension. Here's the dimension is 2. These are these are contractible. These spaces and two-dimensional. And these this is if you map this in here, it maps injectively in. And it follows from homological reasons. There's no nothing, because the dimension here is 2. That's a minimal area filling. You could also use the same proof here to show that a square being filled in, n squared is the lower bound. So we could get our We could get our lower bound for the n squared for this group. Later, yes. Okay, should we take a break? And continue? So, finite groups, they're most linear. Free groups, most linear. Well, it depends what presentation you take. Hyperbolic groups, these can be defined as the groups with linear Dehn function. Well, if you took a stupid presentation, say there's a presentation of F2. You start getting some area. Hyperbolic groups, these, I'm not going to talk about them today, but they can be, except to say that they can be characterized as the groups with linear Dehn functions, or Dehn functions bounded above by constant times n. Well, I'm not sure. Right, you lose an exponential. It would be non-determinate. They're non-deterministic. But you can solve the word problems very quickly for other reasons. Finally generated abelian groups. It's always most n squared. You can get polynomial of any integer degree using freenel potent groups on 2 letters of class C. You get n to the C plus 1. Definitely not. There are all sorts of things have quadratic Dehn functions. SLN 5 over the integers, for example, is a Thompson's group is also an example. Absolutely, yeah, SL5, SLN for n greater than or equal to 5. Starling's group, Thompson's group, all sorts of not monsters, but all sorts of more exotic things can have quadratic Dehn function. It's an interesting. It's an interesting issue. Hyperbolic groups are very special. They're linear. And then there's a gap. There's nothing between linear and quadratic. And you might think, so quadratic's next. You might think quadratic should be special too. But there are all sorts of interesting things in quadratic. Maybe there's still an open question about quadratic is whether you can always solve the conjugacy problem. That's a way in which they might be special. As soon as you go up to n squared log n, you can get groups with unsolvable conjugacy problem. Yes, it's called the Gromov gap. Yeah, no gaps. So I try to think what are the big theorems relating Dehn functions and the word problem. Okay, this one doesn't mention Dehn functions, but it's the sort of father of many of the theorems. So this is Higman's embedding theorem, 1961. You can characterize the finitely generated groups, which are subgroups of finitely presentable groups, as follows. They're the ones that can be presented as like this, where the defining relations are some recursively enumerable set. Amazingly comprehensive theorem, and that built on the technology of this theorem, but I'm putting this one next because it's actually this is the sort of natural main theorem. This can be viewed as a consequence. There are finitely presented groups with unsolvable word problem, and therefore with Dehn function not bounded above by any recursive function. This follows from this, because you could take if you take a function that's recursive but its image is not recursive, then take this group. So this is presented in this manner. The set of defining relations is recursively enumerable because f is a recursive, and you can by Higman you can embed that in a finitely presented group, but the word problem for that you can't solve the word problem for this group. I can't explain to you exactly why, but essentially because it comes down to this, to recognizing when you're in the image of f, such are the way these defining relations are defined. And so you can't solve the word problem in this, and so therefore you can't solve it in the finitely presentable group that Higman gives you. Because if you could solve the word problem for that, if you could solve the word problem for that finitely presentable group, then that would give you a solution for the word problem for this. I give you a word. Right? No, it's well. Of course, it can be made. Sure, you can make it explicit, but it's not pleasant. The way you go about proving these things is embedding suitable computing machines, Turing machines, or Miller machines, into finite presentations in such a way that solving the word problem. The way Van Kampen diagrams, they have features that look like the runs of algorithms, and those algorithms are the runs of these embedded machines. It's great big monstrous constructions. It's not simple. In semi-groups, you can write down examples that are not too horrible to write down. Well, it's still not easy to see that they're examples, but
you can think about the inverse Dehn problem. It's complicated,
right. Then more recently, Biaget, Olshansky, Rips, and Sapir proved this, that a finitely generated group has word problem in NP if and only if it's a subgroup of a finitely presented group with Dehn function that's bounded above by a polynomial. So this is a sort of controlled version of Higman's theorem. related to that, they did work on your question. What are the possible Dehn functions? Well, look at the Dehn functions that grow polynomially.
Here, if I want to know for a specific case, it so this is
So what do you want to know exactly?
if someone gives me here, go back to here, expect disappear. So I have expected
Mm-hmm.
they want to know if it is happening to the
Mm-hmm. Well, if you could answer this, all it says is if you could answer this question, you'd be done.
So normally I would not know. There is no.
Right. I imagine that would be probably undecidable. Right. Okay. So when is n goes to n to the alpha? For what real numbers alpha is n goes to n to the alpha equivalent to a Dehn function? So this is IP is it's called the isoperimetric spectrum. All of these alphas. This is a countable set because there are only countably many finely presented groups. And it turns out the closure is this. You've got the hyperbolic groups here, the linear ones, and then you've got quadratic and above, and there are no gaps. Supremum. So I'm not quantifying. I'm quantifying over. So this is a Dehn function. So that is. Oh, n to the half would be equivalent to yeah. Right. Oh, I see what you're saying. You're right. N to the half. Right. You're right. You're right. Above 1, this issue doesn't matter. But you're right. As I've defined it, n to the half is equivalent to 1. But yeah. So yeah. Thank you. And so building on the previous theorem of Olshansky, of Berger, Olshansky, Sapir, and Rips, Sapir, Berger, and Rips, they're able to tell you exactly which alphas, at least when alpha is greater than 4. So if alpha is greater than 4, it's such that there exists a Turing machine, there is a constant C, so there's a Turing machine calculating the first m digits of a decimal expansion of alpha in that amount of time, then you're in alphas in the isoperimetric spectrum. And conversely, you're in the isoperimetric spectrum. If you're in there, then there exists a Turing machine that calculates the first m digits in that amount of time. And this is one more, this is one higher exponential. And apparently the gap is because we don't know whether p is equal to np. The reason for the extra one. So very detailed information about what Dehn functions you get, at least n goes to n to the alpha when alpha is greater than or equal to 4, greater than 4. Anyway, so to finish this, before getting back to hydra and Ackermann functions, so it's about the time it takes to compute the first m digits of the decimal expansion. So, this is maybe this is general nonsense, but I find that it's a very compelling relationship here between computational complexity measures and geometric filling functions, natural geometric soap film notions. So we've talked about Dehn functions corresponding to time, specifically time in the sense of this Dehn proof system, and it's non-deterministic time. You should really think of it there. So that corresponds to isoperimetric function. That's area of disks filling loops. You can extend this. If there's another nice geometric notion is filling length. And so if you've got a loop, imagine contracting it in a simply connected space. Imagine contracting the loop down to, null homotopping it down to nothing. It's a lasso, you're pulling it tight somehow. Measure how long the loop gets in the course of that null homotopy. So that's filling length, how long the thing must get as a function of the length of the length you started with. That naturally corresponds to space in the Dehn proof system. So there's time, there's space. There are these, So here we have our nice geometric intuition. We, maybe one could extend this list. I mean, certainly these are so filling functions. You can measure other geometric features of loops and disks. There's the diameter is another natural one, and how do you extend the list on the left in a corresponding way? There are questions about relationships between filling functions on the right. How do they relate to the standard questions on the left? I know you care a lot about lower bounds on the left, and lower bounds notoriously difficult. On the right, we have techniques. We have some nice geometric techniques you can use. This is all general mumbo jumbo, but I feel that more should be made of this relationship. Well, yes. So, but in the Dehn proof, one of the morals of that Higman theorem is that the Dehn proof system is really it's sort of universal in some sense. I know that's a technical word, and I'm using it loosely, but it seems that more should be made of this correspondence.
This space is sort of the connection is loose, but at least maybe space is at least linear.
Right.
Below linear,
I agree. Yeah. Okay. So hydra. What a hydra. If you were in my member seminar a couple of weeks ago, sorry about the repetition, but hydra are these they're free bicyclic groups. So it's a family of groups, GK. You start with free group on A1 through to AK, and then you introduce another letter T, which conjugates the A's in this manner. It conjugates A1 to itself. In other words, T commutes with A1, and it conjugates AI to AI times AI minus 1, at least when I is greater than 1. And so these are very simple, cute little groups. They're free bicyclic. In fact, they're one-related groups. You can. I'm not going to explain why for now, but they're geometrically. This is a free group. This is an automorphism. Yes. Yes. And it turns out this subgroup, HK, generated by A1T through to AKT, that's a free group on these generators. It's a rank K free group, and its distortion is like Ackermann's function. I'll tell you what that means in a moment. And if we use this and build another group, introduce another stable letter P, which commutes with everything in the subgroup, everything in HK. So this is just shorthand for saying introduce the. You could do this by just introducing the relations that say P commutes with each one of these generators. So I'm just writing this for short. Then this is a group, a finally presentable group. Its Dehn function grows like the kth of Ackermann's functions. So why? Well, let me. What's P? Yeah, it's another generator, another stable. It's another generator I'm throwing in. And right, to make P commute with everything in. Let me write up these presentations. What did I call it? I didn't give it a name. So then the next thing is right. This is just shorthand. We put in an extra generator, and we've said it commutes with everything in H. In other words, we just introduced k-more relations that say it P commutes with that, and so on. So why? Well, let me try and give you an idea of why that theorem's true via the k equals 2 example. So that's the group in k equals 2. I'll just use A and B. And you have a Van Kampen diagram like this. So red edges, consider them labeled by A's, and green edges by B's, and purple edges by T's. And so this tells us that a to the 4 times t to the 15 equals at, bt, at, bt, 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 at, bt, 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 right? So in other words, a to the 4 times t to the 15 equals some word on the generators of H2. And if you look at the horizontal lines in this, the words you read along them, along the top is a to the 4, along the next one is a, b, a, b, a, b, that's this, and then along the next one it's that, and so on. So this process is, you can think of this as a process which is Hercules fighting the hydra. So hydra is a word on let's just on A and B, and Hercules fights it. So initially it's a to the 4, the hydra. Hercules fights it by knocking off the first letter, and then the thing regenerates. You know, this hydra was this beast with serpentine heads and multiple heads sprung up. So you knock off the first A, and it regenerates in that A goes to AB and B doesn't change. So you remove the first A, and then that A becomes AB, that A becomes AB, that A becomes AB. So we get that. And then repeat. Remove the first A, that B stays as it is, that A produces another B, that B stays as it is, that A produces a B, and that B stays as it is. And you continue in this manner, you eventually get down to nothing, which means that this sort of diagram completes. And this process, the duration of this battle grows like an Ackermann function, A2, in this case. I'll give a reason why it grows so quickly later. Why? But now take this picture and use it to build a bigger diagram. I'm going to put on some more, another column, another corridor of cells, and then another corridor of cells, and then the mirror image. And now I've got, along the top, I've got a to the 5 times tb times a to the minus 5. Along the bottom, I've got some long word on at and bt. And in fact, it's a reduced word on at and bt. The length of this word along the bottom grows. So if this is length n along the top, replace the 5 by an n, the corresponding word along the bottom grows like a2 of n. And this is the idea of distortion. In G2, the word along the top has length n, but it represents something in H2, But if you want to write it as a product of the generators of H2, you need length A2 of n.
But H2 is removing the generator. Then it's one.
Exactly, that's a good point. Because H2 is free, which I haven't proved for you, it's not obvious, there isn't an alternative shorter path in H2. And so length n in the ambient group corresponds to length growing back like Ackermann function in the subgroup. And now if we take this group, we introduce the stable letter p that commutes with hk, why do we get something with Dehn function growing like the kth Ackermann function? Well, take this distortion picture, take 2 copies of it, and put a corridor of cells through, interpolating between. So we've got this, and then it's this below is the mirror image, and this is these are cells that tell you that correspond to p commuting with the generators in HK. They're hexagonal cells, and the number of them equals the length of this word along here as a word on the generators of the subgroup of HK, or H2 in this case. So the area of this thing, well, it roughly equals the length of this word, and well, that grows like Ackermann's function. And it turns out this is both this can be turned into both a lower bound and an upper bound. But that's the idea. Okay. Right. But these are the biggest ones that are. Well, these are the biggest. I can only be vague. These are the biggest ones that are elementary. These are.
If you take something from which it's you don't get it,
If it's unsolvable. Yeah. I don't know. I don't know. There are some very strange things can happen. You think a group with undecidable word problem would have very fast growing word Dehn function, right? So it's, as I said, but the Dehn function can't be if you've got an undecidable word problem, the Dehn function can't be bounded above by a recursive function. That's not the same thing as saying it grows fast. You could have it be on an infinite sequence of scales. It could grow quadratically, but the scales are very far apart. There are examples like that due to Sapir and Olshansky, I think. Strange things happen. You can have groups where with undecidable word problems, so the Dehn function is not bounded above by a recursive function, and yet on an infinite sequence of scales, the Dehn function is bounded above by a quadratic function. It's just the scales are very, very far apart. Anyway, so theorem, despite having a massive, huge Dehn functions, Ackermann Dehn functions, we can solve the word problem in polynomial time.
This uses the algorithm from the beginning.
Yes. And what this boils down to, in fact, is we can solve the membership problem for HK and GK in polynomial time. The membership problem is find an algorithm which, on input a word on the generators of GK, declares whether or not it represents an element of the subgroup. And the step from these are equivalent is really not a difficult thing. It's Britton's lemma. It's essentially, if you know about that, why these things are why these two statements are equivalent is if you have a word that represents the identity in if w equals 1 in this thing, then whenever p's occur in the word, they occur in pairs. So this is a Van Kampen diagram for this word. The p's must occur in pairs that are connected by corridors of cells that come from this relation, corridors of cells that involve the p's, like the corridor, the yellow corridor that ran through my picture a couple of slides back. So solving the word problem, you just search for these pairs of p's, this pair can exist when the word along the side of it is an element of the subgroup. So searching for these pairs of p's reduces the problem down to the membership problem for HK in GK. And that can be done efficiently, polynomial time, not a problem. So really this is all about the membership problem for HK and GK. The degree of the polynomial depends on K. Yeah. So before I give you an idea of how we do that and why the Ackermann stuff at the beginning is the key tool, let me just give you some more background. So Cohen, Madlener, and Otto, I believe Madlener and Otto are computer scientists. They were actually the first people to define Dehn functions, and they were comparing Dehn function with how hard it is to solve the word problem, because and they came up with examples where Dehn function grows like the kth Ackermann function or grows like the diagonal in Ackermann's function, but you can solve the word problem in threefold iterated exponential time. So, okay, that's bad, but it's a huge gap. Yes, yes. But their examples are all monsters. They're about, that's the type we were talking about before, about embedding machines. And there are also contrived examples, but very more recent, Karlampovich, Myasnikov, and Sapir. For any given recursive function, you can find an example of a group with Dehn function outgrowing that function, but the word problem's decidable in polynomial time. But again, it's about embedding machines. Yeah, yeah. But what if? So whenever a group turns up, which has big Dehn function, natural question is, can you solve the word problem efficiently, quickly? Because the big but recursive Dehn function, you can solve the word problem, but via stupid algorithms we were discussing before that are hopelessly inefficient. So can you find other ways to get at the word problem?
Even if it's smaller,
It's still exponential, yes. Right, I mean, even Z cross Z, the example we talked about where you shuffle letters A and B, if you just searched for all ways to shuffle letters, that would be really stupid. You'd be much better off going through and counting A's and making sure they're equal, the same as the number of A inverses. Yeah. And similarly with B's. And this example we saw before has exponential Dehn function. You can solve the word problem very quickly because this is a faithful matrix representation. So how do you solve the word problem? I give you a word on A's and B's. Does it represent the identity? Translate it to matrices, multiply them together. You can tell me, I expect, how quickly you can do that. Anyway, polynomial, definitely. Yeah.
Yeah. So I don't know work for the free book is not clear when you can do the word problem in God's space, and this embedding idea was
Mm.
just a sign of from the 70s, I think, was
Great
last
here.
year. No, but then you can do not in graph, so you can go model line. Yeah, so it's determined.
Let's go to free.
Well, so I'm saying this idea of embedding into a matrix can save a lot of it's not just in polynomial time, you can do it in block space. Also the example you saw.
Yep. So here are two more extravagant but beautiful examples. Baumslag's group, this one related group, and this group of Higman. This has Dehn function growing like a tower, but Miasenkov, Ushakov, and Won show the first one can be solved. You can solve the word problem in polynomial time, and Dikert, Laun, and Ushakov, the second group, the Higman's group, also in polynomial time, and they use the same sort of things as Dison, Einstein, and me. They use ways to represent integers in compressed manner. They use forms of straight line programs called power circuits, and they have algorithms to compare power circuits. So this is a sort of precursor to the result I'm going to tell you. How do we do the membership problem for HK and GK in polynomial time? Okay, so again I'm not going to explain the algorithm. I'm just going to explain how it works on some interesting, some salient inputs. So let's work in G3 as an example. As G3 and as H3. So we take a word. Is it an element of H3? How do we tell? Here's what we're going to do. First, collect all the T's at the front. That is, shuffle the T's to the left, put through the A's, and as you shuffle them along, you change the A's according to using these relations, right? And collect the T's at the front, and that will blow up the number of A's somewhat, but in fact it only blows up the number polynomially. This is a polynomial growth free group automorphism. Next, we do what we call partition this word into pieces. Now this is dictated. How this works is dictated by the locations of the A3s. A3 is the top rank letter here. We look at where the A3s and the A3 inverses lie in here. A piece is a word that it's a maximal length word, subword, that has the property that if it's got an A3 in it, that A3 is at the beginning, and if it's got an A3 inverse in it, that A3 inverse occurs at the end. So the first piece, so the first piece here is that A3 up to that A3 inverse, and then the next one is up to that A3 inverse, and then the final piece is just an A1. Yes, it would be two pieces. So next we try and push these T's successively through pieces. Well, in this example, it turns out it works. You can push this T squared through this piece to give some product of generators of H3 times some power of T. Trust me, that times that is equal to that. Okay, and then you try and push this power of T, actually just a single T in this case, through the next piece. Again, it works, and it comes out to be a single T, and now you push it through the final one, and convert that to something on the generators of H3 times the power of T, and this turns out to be T to the 0 comes out at the right-hand end. And, well, we've shown actually, yes, this word represented an element of H. Now, what was this a reasonable thing to do? So that cost polynomial. That was polynomial cost. That's fine. Pulling the T's to the front. And this business is problematic. Why is it problematic? Well, one reason it's problematic. I didn't tell you how to do it really. Another reason this is problematic is that you don't actually want to write down the word on the generators of h's that's appearing here, because of that distortion effects that we saw earlier. It could be massively long. If you had to write it down, your algorithm would be hopeless. But the key point here is that there's a lemma behind that says that if your word is going to represent an element of the subgroup, then this process of going through one piece at a time will work. And if the t that comes out at the end is t to the 0, then you've got an element of the subgroup. Okay, but you don't want to write down what's appearing, and also you don't want to write down explicitly the power of t as you're going on, because that could be crazily big. So how do we do this? Well, first I have to admit I lied slightly. We're not going to work with Ackermann functions. We're going to work with small variations, psi functions. So they're defined very similarly to Ackermann functions, as you can see, just polluted with some minus signs and a -1 here. So it's annoying. Okay, we've got psi1 is n goes to n minus 1, psi2 n goes to 2n minus 1, and then the subsequent ones are defined on the negative natural numbers by a recursion. Anyway, so it's very similar to Ackermann functions. Similarly fast-growing, same ideas, but just slightly different. And the key point is that t to the r times ai is in a right coset of the subgroup by t to the s, if and only if r is in the domain of psi I, and in fact s then is psi I of r. So these functions govern when you can push a power of t past an ai to give an element of hk times some other power of t to the s. Okay, and sorry at this point to give you a page of algebra is perhaps unfriendly, but this to me, it's not very difficult. I'll go through it. This shows to me really. Hmm? In the domain of, yeah.
I see the domain, you are right. It's actually phi there,
I think it's correct as written. Yeah. So here's the induction step. It's a bit painful because it's a double induction on I and R, but it's where you really see this recursion appear, and therefore where the crazy growth. This is actually the heart of why the crazy growth comes into these groups. So, right. So t to the r a I equals, well, I'm just going to put in a t inverse at the front and a t inverse at the end, equals that. Now that's t to the r plus 1 times, this is conjugating ai by t, but in the relations, that gives me the relations tell me that gives me ai times ai minus 1 times, and I've still got that t inverse at the end. But now we can push t to the r plus 1 through ai, or that is in t to the r plus 1 times ai by induction is in hk times t to the psi I of r plus 1. So the induction is painful because we're dealing with negative numbers, so adding 1 is the right, is the right thing. Anyway, if you can keep your head through that, you see, inductively you get that, and then that goes through the next one, similarly by induction, and we get the next the next term, and then the minus 1 comes from that t inverse. So this is in here. So that's the induction step. So this is where this recurrence comes from. Okay, so let me finish with one final example which shows how being able to compute with these psi functions, just in the same way as I should explain we could compute with the Ackermann functions, let me try and give you an idea of how that suffices to solve the membership problem, again via an example. So take W to be this word. Is that an element of H3? Well, actually, yes, it is. I can tell you, but its length there is 2 to the 47 times 3 minus 1, because it's actually one of the words of the form I was drawing diagrams for earlier. So we don't want to compute. We definitely don't want to write it down as a. You want lunch? Okay. So first thing we do, we send the t's to the front, which converts. So that converts us to this, and then we partition this into pieces. So the top rank letter, the top index letter is 3. So the pieces look like this. A3 times A2 is the first one, and there you go. You can see them. We've got what? 1, 2, 3, 7 pieces. And we try and push through one at a time, but we're not going to write down. Exactly what words we get. So t times this one. Well, that turns out to equal that, which is an element of H3 times. Well, it's an element of H3. So in other words, H3 times t to the 0. So that's not difficult. Now try and push t to the 0 through the next piece. So t to the 0 times A3, A2. Well, you can write down. It goes through, and what power of t do you get out? Well, it's dictated by these psi functions. You're going through A3 and then A2, so you get that. Because we started with 0, then through A3 and then through A2, and then push that through the next piece, this one, and you get you're applying more psi functions like that, and then try and push that this thing here through the next piece, this piece here, and well, this is H3 times t to the. There's some way of writing down appropriate psi function but it's read off from this word, and there it is. I put the front and then.
It turns into validity whether it's 0.
Right. So you keep going, and then through these last three pieces, and it becomes this. And at the end, it's a validity problem, and then a question of whether you get 0 or not. So validity captures whether this breaks down, whether at any point you don't get whether you fail to be in a coset of H3 by a power of t. That's what validity catches. And then when you've got to the end, suppose it is valid, you need to know whether the power is 0. But that's exactly what one of the algorithm at the beginning does for you.
So it's a little different function, but it's the same.
Yes. Yes.